Deep in the Australian outback, giant metal antennas stand frozen under a sea of cold desert stars. Right now, invisible ripples of energy are crashing down from deep space and slamming into the receivers. A digital readout on an astronomer's computer screen shows that something impossible has just repeated itself. Somewhere 15,000 light-years away, a phantom object in the darkness is pulsing with a mechanical rhythm that breaks the known rules of physics. If you love exploring the deepest, most mind-bending mysteries of our universe with real science and no exaggerated hype, go ahead and hit the subscribe button right now. Turn on your alerts so you never miss another deep space investigation as we uncover what is really out there in the dark. To understand why astronomers are losing sleep over this mysterious cosmic signal, we have to look back at how humans first started listening to the sky. For thousands of years, stargazers could only learn about space by looking through glass lenses and mirrors at visible starlight. Everything changed in the 20th century when scientists realized that stars, galaxies, and gas clouds also produce invisible waves of energy called radio waves. Radio waves are the exact same kind of energy that carries music to your car stereo or sends data to your cell phone, except these waves travel across trillions of miles of empty space. When scientists built giant dish antennas to collect these waves, they discovered that space is not silent at all. It is filled with a constant crackling whisper of natural radio broadcasts coming from exploding stars, magnetic fields, and swirling clouds of dust. In the early 1930s, an engineer named Carl Jansky was working for Bell Telephone Laboratories in New Jersey. He was trying to figure out what was causing static on transatlantic telephone lines, so he built a large wooden antenna mounted on car wheels to track the noise. After months of careful measurements, he realized that a faint, steady hiss was not coming from thunderstorms or local electronics on Earth. The hiss rose and fell with the motion of the stars, coming directly from the center of our Milky Way galaxy, thousands of light-years away. For the very first time in human history, humanity had discovered that the universe was talking to us in radio frequencies, launching an entirely new era of astronomy. A few years later, an amateur radio enthusiast named Grote Reber took Jansky's discovery and went one step further by building a 30-foot metal dish in his own backyard in Illinois. Working mostly at night, when car engine interference was lowest, Reber mapped out the bright radio hotspots of our night sky. He proved that cosmic radio waves were everywhere, waiting to be studied by anyone who had the right tools. Scientists soon realized that optical telescopes could only see a tiny fraction of the cosmos because thick clouds of interstellar dust blocked visible light. Radio waves, on the other hand, could punch straight through the thickest cosmic clouds without being scattered, giving astronomers a completely unobstructed window into the most extreme environments in the universe. For a long time, astronomers believed that natural radio signals from space would always fall into very predictable categories. A star might shine with a steady, quiet hiss of radio noise, or an explosion might create a sudden burst that slowly fades away over several weeks. What nobody expected to find was a signal that switched on and off like a giant lighthouse blinking across the ocean. When something in deep space pulses with extreme precision, it immediately makes scientists wonder if they are watching an ordinary natural object, a totally new type of physics, or something far more unusual. The search for these flashing beacons has led to some of the greatest discoveries in the history of science, but it has also created puzzles that remain unsolved to this day. The very first time astronomers ever found a repeating space signal was in 1967, and the story of that discovery shows just how easy it is to be fooled by the cosmos. A young graduate student named Jocelyn Bell was studying charts of radio noise collected by a massive field of wire antennas in the countryside of Cambridge, England. Night after night, she noticed a tiny smudge of radio noise that repeated with incredible perfection, blinking once every 1.33 seconds. Nothing in human science had ever been seen pulsing that fast or that regularly from deep space. At first, the researchers were so shocked that they wondered if they had intercepted a radio transmission from an alien civilization, even naming the signal Little Green Men 1 as an inside joke. What the researchers actually discovered was something completely natural, but equally terrifying and strange. It was a neutron star, which is the crushed leftover core of a massive star that blew itself apart in a supernova explosion. When a giant star dies, gravity crushes its core into a ball so dense that an entire mountain could fit inside a single teaspoon of its material. These dead stars spin around hundreds of times every second and have magnetic fields trillions of times stronger than Earth. As they spin, they shoot narrow beams of radio waves out of their magnetic poles, and every time that beam sweeps across Earth, our telescopes record a quick flash. Scientists name these objects pulsars, and for decades, they believed they had completely figured out how these cosmic lighthouses worked. Astronomers built mathematical models to explain every single detail of how a pulsar generates its light. According to these established rules, a neutron star can only shoot out radio beams if it is spinning fast enough to generate a massive electric field around its surface. Think of it like a bicycle light powered by a wheel generator. As long as you pedal fast, the light shines brightly, but if you slow down below a certain speed, the light flickers and goes completely dark. In astronomy, this boundary is known as the pulsar death line. The theory said that as a neutron star gets older, its spin naturally slows down, and once it takes more than a few seconds to complete a single rotation, it crosses the death line and its radio beam shuts off forever. For more than 50 years, this rule was treated as an absolute law of astrophysics. Thousands of pulsars were cataloged across our Milky Way galaxy, and every single one of them followed the exact same rulebook. The fast-spinning ones beamed bright radio pulses, while the older, slower ones stayed quiet and dark, just as the math predicted. Scientists felt completely confident that they understood the life cycle of dead stars, believing there were no major surprises left to find in this corner of the cosmos. But deep in the desert of Western Australia, an automated telescope was about to record something that threw 5 decades of textbooks straight into the trash. Did you know that a dead star could spin hundreds of times a second? Or did you think space objects always moved slowly? Leave a comment below with your thoughts, and if you are enjoying this breakdown of cosmic mysteries, hit that like button to help more space explorers find our channel. The first hint of trouble appeared when a team of researchers led by astrophysicist Natasha Hurley-Walker began analyzing data from the Murchison Wide Field Array. This observatory is not a single giant dish, but rather thousands of spider-like metal antennas spread across miles of quiet red desert far away from city radio interference. In late 2020, a student named Tyrone O'Doherty was scanning the sky for brief bursts of radio light when he spotted a bright source that appeared out of nowhere. It flashed with intense brightness for about 60 seconds, disappeared completely, and then flashed again precisely 18 minutes later. This strange object, cataloged under the code name GLEAM-X J1839-10, completely shocked the team. An 18-minute cycle was far too long for a normal pulsar, which spins in seconds or milliseconds. According to the standard deathline theory, any object rotating that slowly should have been totally dead and unable to produce radio light. Yet for 3 months, this unknown object continued to shine brighter than almost anything else in that patch of sky, releasing tremendous amounts of energy before suddenly going completely silent in 2018. When astronomers tried to explain what happened, they faced a wall of contradictions. A star, spinning once every 18 minutes, is rotating far too slowly to generate the electrical charge needed to power a radio beacon. The magnetic field required to produce that level of brightness from such a slow spin would have to be thousands of times stronger than any standard model allowed. Furthermore, the object was located only about 4,000 light-years from Earth, sitting practically in our galactic backyard. If such extreme objects were common in our galaxy, scientists wondered why nobody had ever detected one before. The scientific community was divided over what had just happened. Some researchers argued that it was a freak one-time event, perhaps an old star that suffered a sudden crust quake and released a short burst of energy before dying out forever. Others wondered if it was a completely new type of star that nobody had ever predicted. Because the signal vanished and never returned, astronomers were left with only questions and no way to gather more proof. Dr. Hurley-Walker and her colleagues decided that the only way to solve the argument was to search the southern sky again, hoping to catch another slow blinker in the act. Between June and September of 2022, the Australian array scanned the sky night after night, recording petabytes of radio data across thousands of frequency channels. When the astronomers processed the data, they could barely believe what they were seeing on their monitors. At a location 15,000 light-years away in the constellation of Scutum, another signal was flashing. This new source did not pulse every few seconds, and it was not just a one-time flash. Every 22 minutes, like a giant cosmic clock, it beamed out a blast of radio waves that lasted for 5 full minutes before fading back into silence. Scientists officially named this mystery beacon GPM J1839-10, and it immediately posed a massive scientific crisis. A 5-minute burst of radio waves is extraordinarily long in astronomy, where most pulses last only a few thousandths of a second. Furthermore, the 22-minute gap between pulses meant the object was turning at a snail's pace compared to any regular pulsar. Under every existing equation of electromagnetism, an object spinning that slowly should be completely incapable of generating the power needed to create such a bright radio beam. It was sitting deep inside the forbidden zone below the pulsar death line, doing something science said was impossible. To find out if this was a new phenomenon, or something that had been hiding in plain sight, the team did something brilliant. They dug into old digital archives from major radio telescopes all around the world, looking for any past recordings of that exact spot in the sky. They searched through records from the giant Meter-Wave Radio Telescope in India and the famous Very Large Array in New Mexico, which has been listening to the cosmos since the 20th century. What they uncovered inside those dusty archives left the entire astronomical world completely stunned. The next detail is the piece of evidence that changes everything we thought we knew about this signal. When the researchers pulled up observation logs from 1988, they found the exact same 22-minute pulse coming from that exact same coordinate in space. For at least 35 years, this unknown object had been broadcasting its 5-minute radio pulses into the void over and over again, without ever stopping or slowing down. Human telescopes had recorded it dozens of times across 3 decades, but because nobody expected a natural signal to repeat so slowly, computer algorithms had simply filtered it out as background noise. Think about the scale of what this discovery actually means in real terms. For 35 straight years, through thousands of continuous cycles, this object has been pumping out enormous amounts of energy every 22 minutes. If it were an ordinary star losing energy through its rotation, it should have slowed down or run out of fuel long ago. Instead, it has maintained a steady, unbreakable cadence across decades, challenging our most fundamental ideas about how magnetic fields and compact stars interact in deep space. When scientists calculated the total energy released by this object over 35 years, the numbers were staggering. It has released millions of times more radio energy than the entire output of our sun over the same period. Yet, despite searching with the world's most powerful optical and infrared telescopes, astronomers found no visible star at that location. There was no glowing ball of gas, no bright accretion disk, and no cloud of hot dust. Whatever is driving this radio engine is completely invisible to our regular telescopes, leaving behind only the rhythmic ticking of its radio ghost. What makes this finding even stranger is that GPM J1839-10 is not the only unexplained radio mystery lurking in our skies. While slow blinkers were hiding in the archives, another completely different kind of signal was exploding across the universe at blinding speed. These signals are known as fast radio bursts, or FRBs for short, and they represent one of the most powerful and baffling phenomena ever witnessed by modern science. Have you ever wondered how many cosmic signals might be passing through your room right now without anyone noticing? Drop your answer in the comments below, and take a quick second to subscribe to the channel so you can stay updated on every new deep space discovery we investigate. The story of fast radio bursts began in 2007 when astronomer Duncan Lorimer and his student David Narkovich were analyzing old survey data from the Parkes radio telescope in Australia. As they filtered through recordings from 6 years earlier, they spotted an intense spike of radio energy that lasted for just 5 milliseconds. It was so bright that it completely overwhelmed the telescope's detectors. When they calculated how much the radio waves had spread out on their journey through space, they realized the burst had not come from our galaxy at all. It had traveled across billions of light years of intergalactic space to reach Earth. To understand how astronomers know a signal traveled billions of light years, we have to look at how radio waves move through the cosmos. Empty space is not completely empty. It contains a very thin fog of free electrons and charged particles. When a flash of radio light travels through this thin plasma fog, the higher frequencies travel slightly faster than the lower frequencies. By the time the signal reaches Earth, the high notes arrive a fraction of a second before the low notes. Astronomers call this effect dispersion, and by measuring the time delay between the frequencies, they can calculate the exact distance the wave traveled across the universe. In the single millisecond that this flash occurred, it released more energy than our own sun puts out over 3 entire days. Imagine taking all the light and heat produced by our giant sun across 72 continuous hours, compressing all of that power into a single snap of your fingers, and turning it into a blast of pure radio waves. That is the unimaginable power of a fast radio burst. When the Lorimer burst was first announced, many scientists were deeply skeptical. Some argued it was an equipment glitch, a lightning strike in Earth's atmosphere, or even interference from a nearby microwave oven on the ground. In fact, for several years, scientists at the Parkes Observatory were baffled by strange signals they called perytons, which looked almost identical to fast radio bursts but only appeared during daylight hours. In 2015, after installing new monitoring equipment, the researchers finally discovered that the perytons were caused by staff members opening the observatory microwave door before the timer had finished counting down. The open door released a brief chirp of radio waves that the telescope dish picked up. Once the microwave mystery was solved, scientists confirmed that real cosmic bursts like the Lorimer burst were genuine signals coming from the farthest edges of the observable universe. For several years, the Lorimer burst stood alone as an unconfirmed oddity. But as newer and more sensitive telescopes came online, astronomers began detecting dozens and then hundreds of these blinding flashes coming from random directions across the entire universe. Most of them appeared once in a fraction of a second and were never heard from again. This led scientists to believe that FRBs were the final death screams of cataclysmic cosmic events, such as two black holes colliding, two neutron stars smashing together, or a massive star collapsing into complete destruction. Once again, nature had a surprise in store that broke all the tidy theories. In 2012, astronomers using the massive Arecibo dish in Puerto Rico detected an FRB that did something no one thought possible. It repeated. The source, named FRB 121102, fired off multiple bright bursts from the exact same location in space over several weeks. A cataclysmic collision cannot happen twice in the exact same spot, which meant that whatever was producing these bursts had to be a surviving engine capable of firing repeatedly without blowing itself apart. This discovery kicked off a global race to build specialized telescopes designed specifically to catch repeating signals in real time. In the mountains of British Columbia, Canada, engineers constructed the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME. CHIME has no moving parts. Instead, it consists of 4 massive metal half-pipes that look like giant snowboarding ramps, staring straight up at the sky and recording the entire northern hemisphere as Earth rotates beneath it. With CHIME watching the sky every single day, the catalog of fast radio bursts exploded from just a handful to thousands of recorded events. Astronomers discovered that a small fraction of these bursts repeat on regular, predictable schedules. One famous source, known as FRB 1809-10, fires off multiple bursts over a 4-day window, goes completely silent for 12 days, and then starts the exact same 16-day cycle all over again. It was the first time scientists proved that an extragalactic fast radio burst operated on a periodic schedule. Now, astronomers were faced with 2 massive cosmic mysteries at opposite ends of the time spectrum. On one side, they had ultra-long signals like GPM J1839-10 that pulse slowly every 22 minutes for 5 minutes at a time. On the other side, they had ultra-fast repeating signals from distant galaxies that fire off in milliseconds on 16-day schedules. The central question became inescapable. Are these completely different phenomena, or are they different symptoms of the same mysterious cosmic machine? Before we look at the leading scientific explanations, there's an important clue hidden inside the radio waves themselves that researchers had to decode. When light or radio waves travel through a powerful magnetic field, the orientation of their wave vibrations becomes twisted in a very specific pattern, a process known as polarization. By measuring how much the signal is twisted, astronomers can reconstruct the environment surrounding the source. When they measured the polarization of both the slow blinkers and the repeating FRBs, the results pointed directly to the most magnetic objects in the entire known universe, magnetars. Do you think these signals are being created by extreme dead stars? Or is there a chance we are looking at something completely unknown? Share your theory in the comments right now, and if you find these cosmic detective stories fascinating, take a second to hit like and subscribe so you never miss an episode. To understand what a magnetar is, you have to imagine taking Earth's magnetic field, which is strong enough to gently turn a compass needle toward north, and multiplying its strength by 100 trillion times. A magnetar is a rare type of neutron star with a magnetic field so intense that if one came within 1,000 miles of Earth, its magnetic field would dissolve the atoms of your body and erase the data from every credit card on our planet instantly. These magnetic fields are under enormous tension, twisting and winding around the star like coiled steel springs until the solid iron crust of the star snaps under the pressure. When a magnetar's crust cracks, it creates a cosmic starquake that releases a blinding flare of gamma rays, X-rays, and radio waves. For years, theorists argued that magnetars were the ideal candidates to explain both fast radio bursts and mysterious periodic signals. In April of 2020, their theory received a massive boost when a known magnetar inside our own Milky Way, called SGR 1935+2-1F4, emitted a millisecond burst of radio waves that was identical to distant fast radio bursts, but thousands of times closer to Earth. That discovery proved that magnetars can definitely produce fast radio bursts. But when scientists tried to apply the exact same magnetar model to slow signals like GPM J1839-10, the math broke down completely. A magnetar's intense magnetic field exerts a powerful braking effect on the star, rapidly slowing its spin over thousands of years until it crosses the death line. Once it slows down to 1 rotation every 22 minutes, standard physics says its magnetic engine should run out of voltage, shutting off its radio emissions completely. Yet GPM J1839-10 has been happily pumping out bright radio light every 22 minutes since at least 1988. If it is a magnetar, it must possess a secret mechanism for generating radio waves that no theoretical physicist on Earth has ever written down on paper. Some researchers propose that it could be an ultra-long period magnetar, with an unusual twisted magnetic structure that acts like a complex dynamo, somehow sustaining electric fields long after ordinary theory says it should be dead. But until someone can write a working mathematical model that reproduces its 5-minute burst profile, that idea remains an unproven hypothesis. This gap between theory and observation led other scientists to propose a completely different candidate, a white dwarf star. A white dwarf is the leftover core of a medium-sized star. Like our own sun, after it runs out of nuclear fuel and gently sheds its outer gas layers, white dwarfs are much bigger and heavier than neutron stars. They are roughly the size of Earth, but pack the entire mass of the sun into that volume. Because they are larger, they naturally spin much more slowly than neutron stars, which fits the 22-minute rotation period far more comfortably. The problem with the white dwarf explanation is that ordinary white dwarfs do not possess magnetic fields strong enough to create such incredibly bright radio bursts. However, if a magnetic white dwarf were paired up in a tight binary dance with another star, something incredible could happen. As the white dwarf orbits its companion, its gravity could pull streams of hot gas off the other star, channeling that charged material along magnetic funnel lines and generating intense periodic bursts of radio and X-ray emission. This white dwarf binary model gained massive support when astronomers using Australia's ASCAP telescope tracked a repeating radio transient that fired every 1.4 hours. Detailed optical and X-ray follow-up observations confirmed that the source was an accreting magnetic white dwarf siphoning material from a small companion star. It was a monumental breakthrough because it proved that white dwarfs could act as periodic radio engines, opening up a brand new pathway to explain signals that rotate far too slowly to be conventional pulsars. Another famous example of a magnetic white dwarf system is AR Scorpii, located about 380 light-years away in the constellation Scorpius. In AR Scorpii, a rapidly spinning magnetic white dwarf lashes a nearby red dwarf star with a powerful beam of electrons, causing the entire system to brighten and pulse across radio, optical, and ultraviolet light every 2 minutes. Systems like AR Scorpii prove that nature can build complex electrical generators in space using pairs of dead stars, creating rhythmic flashes that mimic pulsars on much slower timescales. Even with these discoveries, the debate over GPM J1839-10 is far from settled. When astronomers pointed the world's most powerful optical and infrared telescopes at the exact coordinates of GPM J1839-10, they saw nothing at all. If a bright companion star or a hot white dwarf were sitting there 15,000 light-years away, our infrared telescopes should have detected its heat glow. The complete absence of visible or infrared light suggests that whatever is producing this 35-year signal is incredibly dark, small, and cold, keeping its true nature shrouded in deep mystery. To make matters even more complicated, Australian astronomers recently discovered another bizarre object called ASCAP J1935+248, which pulses every 54 minutes. What makes this source truly mind-bending is that it does not just pulse on a single rhythm, it actually switches between 3 completely different states. Sometimes it emits extremely bright polarized pulses lasting tens of seconds. Other times, it produces faint, narrow pulses that last only a fraction of a second. And at other times, it goes completely dark for weeks before restarting its 54-minute cycle. Finding an object that switches between different pulse modes every 54 minutes completely shatters the idea that compact stars operate like simple, steady machines. It suggests that the plasma environments around these dead stars are wildly turbulent and capable of sudden reorganizations. Theorists are now wondering whether the magnetic fields of these stars are constantly tangling, snapping, and reconnecting, creating shifting channels through which radio energy can escape into the void. Here is the detail that keeps astronomers watching these coordinates every single week. Right now, observatories across the globe are continuously monitoring GPM J1839-10 to see if its timing shifts even by a single microsecond. If the object is slowly spinning down, measuring the exact rate of that slowdown will reveal the strength of its magnetic field, and finally, tell us whether it is a bizarre magnetar or something humanity has never seen before. To understand why this timing is so critical, imagine watching a clock that loses 1 second every million years. By tracking that tiny shift, scientists can calculate how much energy the star is losing to the surrounding space. If the star is spinning down rapidly, it means an enormous invisible magnetic field is dragging through space like a giant brake pad. If it is hardly slowing down at all, it means the star has almost no magnetic braking, which makes the presence of such powerful radio beams even more impossible to explain. Every single week, new data pours in from telescopes across the planet, from South Africa to Europe to the Americas. Scientists use software to stack these pulses together, searching for tiny subpulses hidden inside the larger 5-minute wave. What they are finding inside these pulses is a rich, complex structure of microbursts that flicker on timescales of milliseconds. This means that inside the giant 22-minute engine, smaller electrical sparks are snapping and crackling, creating a symphony of radio frequencies that we are only beginning to decode. Could these microbursts be the key to cracking the code of how stars generate energy? Or are we missing an entire branch of physics? If you want to stay on the front lines of breakthroughs like this, click the subscribe button and give this video a thumbs up so more people can join our journey through the cosmos. The implications of these discoveries go far beyond just cataloging strange stars in our galaxy. When radio waves travel across thousands or millions of light years, they interact with the invisible web of matter that fills the universe. By analyzing how these waves are bent, delayed, and magnetized during their journey, astronomers can use these signals as natural probes to weigh the universe itself. They can measure how much ordinary matter exists in the cosmic voids between galaxies, solving long-standing puzzles like the missing baryon problem that had puzzled cosmologists for decades. Furthermore, the discovery of repeating signals with ultra-long periods has forced scientists to rethink how they search for signs of intelligent life in the universe. For over half a century, programs like the Search for Extraterrestrial Intelligence, or SETI, have scanned the sky listening for narrow-band radio signals. Most search algorithms were designed to look for signals that pulse very rapidly, assuming that advanced alien technology would transmit high-speed data streams. The discovery that nature produces powerful signals pulsing on timescales of minutes or hours means our automated filters may have overlooked hundreds of candidate signals simply because they were too slow. Astronomers at the SETI Institute and the Breakthrough Listen project have now updated their computer algorithms to scan for ultra-long transient signals. While nobody claims that GPM J1839-10 is an alien transmission, studying its extreme behavior ensures that if an artificial beacon ever does broadcast from deep space, our telescopes will not accidentally dismiss it as background noise. Every time we refine our ability to distinguish between natural cosmic engines and artificial signals, we sharpen our tools for the ultimate search for life beyond Earth. As we look at the bigger picture of these hidden signals, a profound realization begins to take shape. For centuries, humans looked up at the night sky and assumed that the stars were quiet, static points of light that changed only over millions of years. But our modern radio telescopes are revealing that the cosmos is alive with dynamic, pulsing, and transient energy that flashes in milliseconds, minutes, and days. We are living in an era where automated sky surveys are discovering thousands of these cosmic beacons every single year, transforming our view of the universe from a quiet photograph into a bustling, energetic movie. New megatelescopes currently being constructed, such as the Square Kilometre Array in Australia and South Africa, will soon link thousands of dishes across 2 continents. When these arrays reach full operational power, they will be capable of detecting radio signals millions of times fainter than anything we can hear today. Astronomers fully expect to uncover hundreds of slow-pulsing objects and tens of thousands of repeating fast radio bursts scattered across every corner of the sky. Each new signal we record is another piece of a massive cosmic puzzle, forcing us to refine our understanding of matter, gravity, and electromagnetism under the most extreme conditions imaginable. Engineers are also designing future observatories to be placed on the far side of the moon, where thousands of miles of solid lunar rock will shield the instruments from all human radio noise on Earth. A lunar radio telescope would be able to listen to the ultra-low frequency radio universe, a completely unexplored spectral window where the earliest stars and the slowest cosmic blinkers broadcast their secrets. Such an observatory could finally reveal the true nature of long-period transients and open up a brand new chapter in our exploration of the cosmos. These mysterious signals also serve as an important reminder of human curiosity and humility. Whenever we look out into the dark and see something we cannot immediately explain, our first instinct is to wonder if someone else is out there transmitting a message across the stars. While nature almost always turns out to be responsible, the natural engines powering these signals are far more spectacular and violent than anything science fiction could easily invent. A single collapsed star spinning in the desert of space, defying our laws of physics for decades, teaches us that the universe is far stranger, richer, and more wonderful than our current theories can capture. Every time we point our dishes toward the sky and catch another impossible pulse, we are taking one small step toward decoding the fundamental machinery of the cosmos. The signal 15,000 light-years away in Scutum will pulse again 22 minutes from now, just as it has every day since 1988, waiting for us to finally understand its message. If you enjoyed uncovering the truth behind this 35-year cosmic mystery, make sure to hit that subscribe button right now and click the notification bell so you never miss our deep dive space investigations. Leave a comment below, letting us know what space mystery you want us to investigate next, and share this video with a friend who loves the unexplained wonders of outer space. Thank you so much for watching, and keep looking up at the stars.